All right, guys. You guys have the lights on or lights off? You don't care? No? All right. Good. I know, right? All right. So fundamental theorem of algebra, which sounds very basic because you guys have done so much algebra at this point, but we're going to be present to that. Linear factorization theorem, that should be pretty straightforward. Complex conjugate zeros theorem, which I think you've seen before. So the fundamental theorem of algebra, guys, quiet, please, purely states that whatever your degree is, that's the number of zeros you have, regardless of they're real or not real. So obviously the real zeros may not match a degree because sometimes we have like a cubic function that does this. Yeah, what's up?
Just one last question.
Yeah, far. Yeah, go. Yeah.
Um, it said list the rational zeros, also list any irrational or non-real zeros. Were there any?
Oh, for the homework we just had? I don't know. I don't think so. Doesn't look like it. Oh yeah, there was an irrational for number 6. 1 plus minus root 6.
Oh, oh yeah.
That's if you quad form, if you're quadratic.
And no,
I don't think so for the other ones. No, no, not at all. Yeah, because some of them have multiplicities. Yeah, that are more than one. Yeah, we're good. All right. All right. So anyhow, if you have a cubic function, right? Like maybe your cubic function crosses the x-axis once, but it's still gonna be 2 more zeros. They're just not real. That could happen sometimes. Or like a quadratic. The quadratic may just completely miss the x-axis, so it's gonna have 2 imaginary zeros. So the bottom line is this: the fundamental theorem of algebra tells us that the number of zeros, whether it's complex or real or not real, equals a degree. And some might be repeated, perhaps. Okay, the next thing. The factor extends to the complex zeros of a polynomial. K is a complex zero of if and only if x minus k is a factor. And usually when you write it as a complex number, if k were if k equaled a plus bi, by the way, how would you write? You write as x minus parentheses a plus bi. If k were a complex number, just so you know. And by the way, we're going to talk about this later today. If you have all real coefficients and one of your Kieran, I know Emily, I know you guys are probably talking math. I need you to focus. Thanks. But if you have all real coefficients, we'll talk about this on the next page. All real coefficients, and one of your zeros has an imaginary number. What else must we expect? The conjugate. So you need that as well. We're going to talk about that later today. But again, if k is a imaginary number, you still write as x minus k, but because it's no pun intended, it looks more complex. A plus bi, you got to do x minus that in parentheses. So, linear factorization theorem. So if your degree is n, then we'll have n linear factors, even if some are repeated. So the way we write is x minus z1, where z is the first zero, x minus z2, that's the second zero, times dot, dot, dot. And you just keep going until you've exhausted it all, until you get to x minus zn and 0. And again, some might repeat. They're not necessarily distinct. Some might be repeated, as you see right there. So, for example, what if you had as 1 is 0, and that has multiplicity of 2? Then x minus 1, x minus 1, and so forth. So we don't see that over here, obviously, but yeah. So that's just called the linear. So linear factorization theorem is how it sounds. You want to write the function as a bunch of linear factors. And by the way, so that question you have about 3x plus 1, actually the proper way to write would be x plus 1/3 or x minus negative 1/3. And then the leading coefficient is just pulled out. So even though it looks kind of weird on the inside, we go with it if you're doing the linear factorization theorem and you deliberately force the leading coefficient out. Even if it causes fractions, you still force it out. So does it make sense how the linear factorization theorem is set up? It's just basically writing the function of a bunch of linear factors. Even if they're complex, so be it. Or even if it has if you have a quadratic that's really wacky, like let's say I have something like this here. Is that factorable? X squared plus 2x plus 5? No. But still, let's do quad form. Let's do quad form. Let's get the wacky answers and write x minus each of those wacky answers. We'll still do that. That's what linear factorization is. Even if it's not reducible, we're going to force the issue. Of course, this one's already factored. Okay. So asking to multiply it out. Okay. That's not hard. And that's just FOIL. You guys know that. Likewise for part B. Let's take a look at these two. These are probably the easiest to FOIL. What would that be? Okay. And of course, it's x minus 5. In standard form means you have to go a little more. You should get that. That's a plus 2x, by the way. My handwriting sucks. Sorry about that. Is that a little better? So that makes sense. Before I move forward, all I just did was FOILed the imaginary number parts first. For I is I squared. What's I squared again? Okay, positive 2. Minus 5. Yeah. Okay. We good? Okay. Why don't you guys try part B? I'll do as well, and then I'll unfreeze when I'm done. Probably want to fold the first two and last two, then bring them together afterwards. Good? We're okay? And by the way, that's a degree 4. So it could potentially cross the x-axis 4 times, or have 3 peaks and valleys or experiment. But of course, there's only 2 real x-intercepts, just 3 negative 3. So it only crosses the x-axis twice if you were to graph this. This is why we're kind of spending time doing this stuff, because when we start applying calculus principles to these functions, right? I'm expecting this graph to cross the x-axis just twice. What's the y-intercept, by the way? What would the y-intercept be here? And does this have even rod symmetry or neither? What do you guys think? Even, why? You have 2 squared terms and you have a constant. Yeah, 100%. What's my end behavior gonna be like? Both arrows up or down? Yep. And there's no bouncing. So it actually is going to flatten out over here because of the symmetry. So even though it's not truly a parabola, it kind of looks like one a little bit, right? Yeah, that's what I expect. So, and you can see it's increasing for a certain time, decreasing, right? So decrease until to get to 0, increase until x bigger than 0. All right. So this just helps us to get a better idea of how these graphs look without the use of technology. Okay, next up, complex conjugate zero theorem. So we did fundamental theorem of algebra. So remember, the degree equals the number of zeros, whether it's complex or real or imaginary. Linear factorization, just x minus the zeros, right? They could be repeated and do that for the imaginary or whatever, or rational. Complex conjugate zeros. Now, if all your coefficients are real, okay, if all of them are real, and assuming a and b are real numbers, so a plus bi could be a 0, then its complex conjugate, a minus bi, is also 0. That's because you don't want, because if you don't do that, you will get an imaginary coefficient. So you have to make sure you do the conjugate to guarantee real coefficients. It only applies if you have real coefficients. So like in this case, write upon a function in standard form. And when I say of minimum degree, because you could technically repeat these zeros as often as you want. I could have negative 3 show up 10 times if I wanted to. Don't do that. It's crazy. So yeah. And by the way, I didn't say what the leading coefficient was. let's assume A equals 1. Let's assume the leading coefficient is 1. So let's not worry about it. Now, if I do give you a point on the curve, and I want you to solve for A, then by all means, plug in that point and solve for A. But I'll specify what's going on with and that's kind of confusing because it's A plus BI. Let me rephrase that. Assume the leading coefficient is 1. So that's what I meant to say. Because A is also part of the complex number. That's a little confusing. I meant A like that, but just assume it's 1. Okay. What's gonna be the other factors? Yeah, x minus 2 minus I. And x minus 2 plus I. Okay. Well, what do I do? What do you think is the most efficient way to well, this can get really nasty with the foiling. Any thoughts of some shortcuts or organization techniques? Yeah, what you could do is that, so go Tom, say again. Yeah, so you could just show that minus, right? So it looks like this. We probably should do that as a first step. Does that make sense? Okay, now, when you combine these two groups, you'll generate 9 terms, right? X times each of these three, -2 times each of these three, positive I times each of those three. That gets nasty. And then you gotta simplify that. And then you gotta still do this. And then you gotta still multiply afterwards. You can do all that work. I'm gonna show you a better way. Because you could just go through all this and get 9 terms. And that is crazy. I wouldn't do that. So what would I suggest instead? You could do a couple things. One thing you could do is you could regroup it like this. Why I think I'm doing that? Oh, sorry. We'll go Sean first.
You can just do, well, basically what you're saying, you can do your difference doing x minus 2 squared.
Yeah, so what you could do is you can do a difference of squares. Like, for example, when you guys saw this stuff back in the day, like A plus B, A minus B, you don't have to write this down. Do you guys know what that would become? Yeah, I didn't have to bother the inner or outer terms. Because what happens in inner and outer terms? Yeah, when I get like AB and negative AB, if I work this out. So by writing it in this fashion, if I do x minus 2 to the group times negative I, x minus 2 is the group times positive I, I'll have negative I x minus 2, positive I x minus 2. Those will cancel out. So really I'm just doing x minus 2 x minus 2, and I have negative I. You can do it that way. And if you do it, here's how it looks. It looks like this. X minus 2 squared, negative I x minus 2, positive I x minus 2, and negative I squared. What do you see is happening with the middle terms? Negative I x minus 2. Yeah, exactly. And remember, negative I squared is that. So what do you get? X squared minus 4x plus 5. Right? It's pretty nice, huh? Let me change colors so you guys can see a little better. Is that okay? Okay, what about the other group here? What's that going to be? I'm just going to kind of go fast. Does that make sense? Then you got to foil that, the blue with the brown. I think it's brown. So then you have to, let me erase some stuff here because I need some space. Okay, and then you gotta do one more time. Now you could go about this a few ways. One way you could do this is you can make a table. You guys remember this like box thing? You guys ever foil that way? Does some of you guys do that? Yeah, you could do that. X squared, negative x, negative 12, x squared, negative 4x, positive 5. So you should have x4, negative 5x cubed. If I go along the diagonals, negative 3x squared plus 43x minus 60. You get that, Kieran?
Yeah.
Okay. Okay, good. We're in agreement. So notice what I just did here. Okay, now you're not technically foiling, because foiling is actually for two binomials, first outside, inside, last. I just use that term loosely. If you do too, that's fine. But what you're doing is you're actually multiplying two trinomials. 9 terms, right? So you can do x squared times h is 3, negative x times h is 3, negative 12 times h is 3, which of course you're doing in the box. But the box keeps all organized, which is kind of nice, right? So hopefully it reduces the likelihood of careless mistakes. Just careless mistakes that happen very easily here. Of course, it'll be incredibly forgiving. You make a mistake here, but you got all the other stuff right. Yeah, I'll give you most of the points, but you know, if you can avoid that, why not? So anyway, that's the way you can do it. Now I'm gonna give you another technique you can use. Yeah, another way. But does that make sense what I did? We're okay with that? With all the foiling? Okay. Here's yet another technique, and I'll leave it to you if you want to do it. Can we have this right here? If you think about it, where did it really come from? It came from this, right? Right? Isn't that a true statement? Doesn't x equal 2 plus minus I? Like, what if I gave you the equation and asked you to solve it instead? If I gave you the equation and asked you to solve it, you would get that as your final step. What if you reverse engineer and go backwards, or go from bottom to top? So what if I did this? F of x equals all this junk, and your final answers are this, right? Well, if you think about it, if those are your final answers, I'm going to go backwards. What would be the factor for x equals negative 3? X. Wouldn't that be true? What would be a factor for this? Wouldn't it be true? And what's happening over here? Isn't that just going to be x minus 2 equals plus minus I? Wouldn't that be a true statement if I would go backwards? And then wouldn't this be a true statement? And wouldn't this be a true statement? Because if you square positive or negative, it's still positive, but I squared is negative 1. And then, oh, look at that. What do I got now? I got x squared minus 4x plus 5.
How do you know the square?
Well, sorry, say again?
How do you know the square?
Because I want to get rid of the I. That's why. I don't have I. That's why. And of course, you have x plus 3 as well. Then you still have to foil regardless. I mean, you still have to do that. But it's yet another technique you could use too, just so you know. But I would not just like take distribute the minus into the complex zeros and then generate 9 terms with I in them. It's just too much. I don't know if I'd do that. So you have this video you can always rewatch if you need to. All right. Oh boy. Yeah, what the heck, let's do it. So you have x minus 1. You can have x minus parentheses 1 plus 2i. X minus parentheses 1 minus 2i. X minus parentheses 1 minus I. x minus parentheses 1 plus I. All right, have at it. I'll do it as well. I'll give you a few minutes to do that one. Before we move on to pages 15 to 16. By the way, you don't have to put in standard form. Just put it in factored form. So here's what I want you to do. Combine these first two here. Combine these two, but don't. So then your answer will look like this: x minus 1, then x squared plus dot dot dot, x squared plus dot dot dot, and leave it like that. Don't boil all that further. That's not necessary. That's busy work at that point. So what I want to do is combine these two with a 1 plus 2 and 1 minus 2 and 0 to 1 minus 1 plus I. Combine this, okay? I do have the answer if you want to start checking your work. Yeah, so you see how it got regrouped? X minus 1, x minus 1, x minus 1, x minus 1. Negative 2 with x minus 1, positive 2 with x minus 1, 5 with x minus 1, negative 5 with x minus 1. Things cancel. You have all that work. Yeah, so.
Let's see. I already said it back in the.
What was that? Oh, it does? Okay. Okay. Well, these are old. I didn't make these. These are just old notes. So, okay. So you leave like that. That's all good. Any questions? No? Cool. Okay. Let's move forward. All right, can I move on? All right, let's move on. All right, example 4. So now let's go back to the equation in standard form. That's right in linear factorization. So we have to find the possible rational zeros. So we got to do the P over Q business. So this is on page 15. So how would I find the rational zeros? What would they be? Yeah, right. All over plus minus 1. Okay. So I'm not going to make you do trial and error. Okay. We should use the graphing calculator. So actually, even though I'd love to use Desmos, I'm going to use the graph calculator instead. Okay, where do you think it's crossing? What do you guys think? -2, 1, and 4, looks like. Yeah. So it looks like we'll have x equals -2, 1, and 4. So now you got to break it down, right? Break down to smaller factors. Use synthetic division. Use long division, I think that's crazy. Use my box method, but I think synthetic division is going to be faster. So 1, -3, -5. Remember, any terms that get skipped over, make sure you put a plate 0 as a placeholder. And you can start with any of those 3 that you want. And I'm taking faith that they're not like weird decimals, like they actually were those numbers. So bring it down. Cool. Good so far? Okay, continue breaking it down. Oh, okay, I did something really dumb. What did I just do, guys? What did I do? Yeah, so it happens. We get carried away. Now, would -2 have been a good choice if what happened in the graph?
Good balance.
Yeah, if it bounced and you know to do it twice, yes. Of course, is there any bouncing here? No. So that's okay. So in that case, yeah, let's do the other one. Let's do 1. I knew that something seemed off because the number's just getting too large, right? Okay, now in this case, I can synthetic division one more time. Bless you. But you know what? I can do factor by grouping, right? I can regroup to get this. Are you guys familiar with this kind of factoring? Factor by grouping? You can do synthetic division if you want to again. But at this point, I need some space now, so I'm gonna erase. And by the way, I'll give you a calculator for this, or I'll give you the zeros. At this point, you get this, you get this, you get this. So you have 5 answers, right? Where are your 5 answers? Plus or minus I, 4, -2, and 1. Okay. 5 answers? 2, right?
Oh,
Three,
yes.
4, yes, 5.
Yeah.
Okay. Cool. All right. So let's try this again. Now, if 1 minus 2 is an answer, here's what you're going to do. 4, 0, 17, 14, 6. Now, can you find the P and Q stuff? Sure. But if you're given a 0, and I would probably put this as a non-calculator question. If you need a 4-function calculator, there's just math those sometimes crazy. I'll be okay with that. Hold on. I'll still work. Can I take a leap of faith here? This might be kind of nasty. Yeah, I think it might see where I'm going with this. Do you guys see what I'm doing right now? I'm dividing out 1 minus 2i. So it'll be 4 minus 8i. Okay, then what would I do next at this point?
Yeah,
At the-
well, too.
Yeah. And then I have add those 17. Yeah, I don't like this. Okay, here's what I'm gonna do instead. Here's what I'm gonna do instead. I got you guys here. I got you guys. We know this is true, right? But we know this is true. And it's still gonna be two more zeros. Z1. Right? I know this is true. So what if I were to combine that, right? Like this. So I'm glad I started synthetic division to show you that it was kind of it would still be fine, but just be crazy. So if I were to do this, I should get x minus 1 squared minus 4y squared. Notice I didn't waste my time doing 2y with x minus 1, negative 2y with x minus 1. I know they're going to cancel, right? So we've done this already. If I clean it all up, I should get this x squared minus 2x plus 5, right? Now what I'm going to do, I'm going to do f of x divided by, I'm going to do that. Now, if I do that, you could do polynomial division, Bond division, or use my box method, whichever way you like. I'm using my box method because that's what I want to do. But if you want to do long division, go for it. But I'm going to do the box method instead. Does that make sense where I'm going with this? Right, that makes sense, hopefully. So when I do that division, and because I expect this to come out clean, I should not have to worry about remainder. Oh, bless you, by the way. And that's 4x4. Now, what do you multiply to x squared to get the 4x4? Okay, that's negative 8x cubed. And that's 20x squared. Okay, do we have an x cubed and f of x? So what do you need to balance it out? Good, you guys are getting the box method. I love it. So it has to be 8x. Okay, it has to be 8x. So negative 16x squared and 40x. Okay. Do I have an x squared? I do. 17. Right now, this adds up to 4x. So I need 13 more x squares. So that's 13. Negative 26x, which combines nicely with that. 65. Oh, yeah, look at that. That is so nice. That's lovely. Okay. 14x, 65. Boom. Nice. That's your new polynomial. Unfortunately, that's not factorable. So I'll quad form it. And it's imaginary. So I will give you a calculator because you know what? Calculator's not going to help you anyway. You're getting more imaginary answers. So this never crosses the x-axis, by the way. What's 8 times 13? Is that 112?
Times 2 AC.
Minus 2 AC. Oh, minus 4 AC. Oh my God. Yeah, I teach math. Oh my gosh. Minus 4 AC. Okay. I need winter break to come soon. All right. 16 times 13. 16 times 13. I am not going to do that in my head. I get 208, 64 minus 208. I get, oh, that comes out lovely. Look at that. You get negative 144. That's negative 8 plus or minus 12i. So that's just negative 1 plus or minus 4/3, I think. So is that fourth? No, 3/2 i. Yes. Right. So your other zeros are negative 1 plus or minus and of course you have 1 minus 2i and 1 plus 2i or 1 plus minus 2i. Now to write the linear factorization, I'll do it down here. That'd be your final answer. So you have those zeros in purple, and that's the linear factorization right there. Yeah, that's a pretty advanced problem. Let me show the solutions so you guys can see it. Yep, here we go. We were supposed to linear factorization for the other one, but oh well. What were we supposed to? Yeah, whatever. It's fine. I didn't, for example, you guys get the idea. Okay, cool. Yeah, you can see what they did, or they, the previous teacher. They did kind of go about this way. If you want to, you could have. Actually, I think the same amount of work, actually, more if you got. I don't know, it's up to you. If you want to go about this way, you could have done this also. You have access to this, these fill out notes in Schoology, or you can just do the box method by dividing. It's up to you. I guess it's all the same, I don't know. Because it should come out clean, right? Because it's a 0. Using the factor theorem or remainder theorem. Okay. Last bit, we're almost done here. Because definitely that's a little longer than I thought, but that's okay. Okay, you may have noticed that every time you FOILed out 2 linear factors, each contain one pair of a non-real complex conjugate members, always result in quadratic polynomial, which contains only real coefficients. This is also called an irreducible quadratic expression. Because if you were to try and factor it, you cannot do it with real numbers. So every polynomial function with real coefficients can be written as a product of actually, yeah, linear factors of linear factors and irreducible quadratic factors with real coefficients. Irreducible quadratic factors with real coefficients. And polynomial functions, every polynomial function of odd degree of real coefficient has at least one real 0. Because the complex zeros have to come in pairs. So we just saw in the last example, we had 3, 4. We have all 4 imaginary solutions, right? But if you have an odd degree, as it says here, and all coefficients are real, well, of course, 1 0 has to be real, because you can't have 3 imaginary zeros, because the imaginary zeros have to come in pairs. You can't have real coefficients, just say that. Irreducible quadratic. Yeah, let's just do this here. I'm gonna get lazy. Here we go.
Also,
I misspelled it, by the way. I misspelled irreducible. Actually, I don't know if that's spelled correctly. Irreducible? I don't know.
It's even better. There's like fold irreducible.
Okay, maybe. You know what? I'm not going to question it.
well, it's written right up there,
Yeah,
right
exactly.
above it.
Yeah.
In the bold.
Okay. So I want you guys to try example 6 on your own. What I'm going to have you use user graphic calculators. If you don't have one, you can use Desmos, it's fine. Identify one of the rational zeros. Break down the polynomial after you break it down, continue to break it down and write it as a product of linear and irreducible quadratic factors. You don't have to write as all linear factors. If it's a quadratic not reducible, it's not factorable, leave it as is. Okay. So let's do this. We'll spend about 5 more minutes. And you guys should have time to work on homework after that.
I already get this. There's only one. No, there's 3 real ones. I don't know. That's right.
Ah, I'm off. 9:40, 10:10.
Plus or minus. But so how do you do it? What I'm doing is when you first. And then I'm multiplying x minus root 2, x plus root 2, and then dividing.
35.
Because this root 2.
But if you just do it, I'm just guessing.
Yeah, I guess. I don't really know. That's a discussion. It's just like.
That's 20.
I'm not trying to get so I know that one of the answers is negative root 2, I know it's positive root 2. So what I can do is I can multiply them together and get what they're like, whatever they're multiplying together. And then I can divide this rest, because I know that there has to be another 0. There's gonna be some irrational 0. So I can divide it by, I guess. It's already divided by.
So you do all of it, so you're doing this divided by x plus root 2 times.
Oh, I also did the math.
Okay, you guys get 2/3 as one of the zeros. Yeah, that's why you definitely need a calculator. Yeah.
Yeah, which, is it like this, or is it? Like it works. Oh, no, not doing it.
I don't know if this is.
I don't know if you answered that one.
This. It's too high. I don't know. I actually, I don't know. I got
History. I don't remember.
I think that's too regular.
Negative 2/3 for the homework. Number 2. 2/3 should work. Yeah. Yeah, 2/3 works. It doesn't? It's actually the same as the notes. Yeah. Yeah, exact same problem. Did you punch it wrong in the calculator? Yeah, guys, this is number 2 of the homework. So you got number 2 done for you guys. Okay. So any questions on this? Yeah, by the way, this is really number 2 of the homework. So you don't have to do number 2 of the homework. Not necessary. For some reason, the answers have the linear factors, all linear factors, but seriously, you can just write it like this. I'd write an answer like this: 3x minus 2. To me, that's good.
You know, this is plus or minus.
Yeah, to me, that's good enough.
I don't understand that. What even, okay, realistically, I feel like this is guessing. I get.
Yeah, I don't know why this is broken down. So
But
I guess
This
it's
plus or minus
irreducible if you have imaginary zeros.
I just divided.
Yeah, but if you have irrational.
I had the rest of the remainder from this.
I guess technically speaking, irreducible is only when and so this is imaginary zeros. But I just think it was more just with
Okay, my answer is that.
so next.
That's the correct answer. Look at the top, x minus 2.
Okay, you guys could get a head start on homework. Just homework number 6. All right, I'll leave this up. If you guys are still looking at it, I'll stop the recording.
Okay, I get there. Yeah, you're reducing that.